Good, how are you?
Good. So what do we got going on tonight?
Logs.
Okay. Love them.
Yeah.
Actually, I do kind of like logs. I mean, I like tutoring logs. Logs and exponentials.
Okay. So basically, I think I know how to do it where it says, like, evaluate each.
Okay.
So it says, like, log 2 and then 4.
All right.
And then you just set that equal to x, right?
Uh-huh. When they say evaluate that, the best thing to do is to go ahead and add the variable. And now converting from log to exponential expression. What is the exponential expression of that log expression?
2 to the x equals 4.
Yeah. Now you can solve it easily. X has to be equal to 2. Therefore, log base 2 of 4 is equal to 2.
Okay. So then how do I do it if it's like log 2 and then parentheses 2 to the 10?
Like that?
The 10's outside of the parentheses. I don't know if that changes anything.
Not really. Okay. There are 3 basic log rules that you really have to remember. Let me write them at the top here. You have the log of the product of 2 things is equal to the sum of the logs. You have the log of the quotient of 2 things equaling the difference of the logs. And finally, you have the log of a to the b power is equal to b times the log of a. So this problem again was the log base 2 of 10 squared, like that. Oh, no, it was 2 to the 10th? Well,
Yeah.
so which rule would I apply? Rule 1, 2, or 3?
Rule 3, the power rule.
Yeah. So this is going to be, in other words, I can bring the 10 down on the fraction line, so it becomes 10 log base 2 of 2. Well, the log base b of b is always equal to what number? In other words, what's the log base 2 of 2? It's 1. Always 1.
Oh, okay.
Notice that if I said evaluate this, you would put the x over there, and then you would have 2 to the x equals 2. Well, x has to be 1.
Oh, okay.
Okay? And it's always that way. In other words, the log of base 17 of 17 is 1. So I can replace that with a 1, and my answer is 10. Now, regarding these 3 rules, they want you to go both ways here. They want you to be able to expand an expression, and they want you to be able to condense an expression. So you have to be equally good at going from right to left as left to right.
Okay.
What else you got?
Alright, so what if it says like log 6 of 6 square root 6?
Like that?
Yeah.
Okay. Well, so we have 6 to the x is equal, well, what is 6 square root 6? That's 6 times 6 to the 1/2.
So
6 to the 3/2. Right? In other words, when you multiply same base, different exponents, you add the exponents. Now I have 6 to the x equals 6 to the 3/2, therefore x is equal to 3/2.
Okay.
Okay. So let me just give you a quick drill on if I have 8 equals 2 cubed, give me the logarithmic expression of that.
So that's log 2 3 equals 8.
Remember one word. Logs are exponents.
So log 2 8 equals 3.
Yeah. In other words, if you remember that, you don't have to remember anything else. If you remember logs are exponents, then I can write that much of it, right?
Right.
And this is always the base. Whatever's being exponentiated is the base. So there's only one other place to put the 8, right there. So you want to be able to go back and forth between these equally as well also. Because a lot of times when they say evaluate this, you have to put it in exponential format. So you definitely need to be able to go from log to exponential, but also from exponential to log.
Okay.
Okay? All right, what else you got?
Log.
Actually, I had a student earlier today that had a log problem that was really hard. I couldn't figure out how to do it at first, and that's rare. I'm pretty good with logs. But I don't know if you have quite the degree of difficulty. What school do you go to, Jay?
Columbine.
You might. The problem was pretty cool. The problem was 4 to the x plus 2 to the x minus 12 equals 0. Have you had to handle anything like that?
No.
Okay. Well, I won't go there, but it's a quadratic in disguise. Go ahead. What are you guys working on?
Log 6, and then cube root of 1/6.
Now, you can use radicals, but when you're dealing with logs, it's much better to use exponents because of that feature that you can always bring the exponent down. So I don't want to write that as cube root. I want to write that as to the 1/3, like that. Okay?
Okay.
So we know that that's equal to what? Let's simplify it first.
That's equal to 6.
Well, it's equal to 1/3 times the log of 6, like that. Right?
Oh, yeah.
That's first step. Now let's work with this. Evaluate that. That means 6 to some x equals 1/6, right?
Right.
So what would x be? Minus 1. In other words, what does this mean? That means take the reciprocal of it.
Ooh.
Let's review. What does this mean?
So 2/3.
No? It's the reciprocal. It's like that. In other words, that's all negative exponents mean. They don't mean negative numbers, ever. They mean reciprocal.
Okay.
Okay, so that number is 1/9. And 6 to the x equaling 1/6, x must be minus 1. Because 6 to the minus 1 would be 1/6 to the 1. In other words, the negative exponent merely means the reciprocal with a positive exponent. So this whole thing that I have circled up there is minus 1, so therefore the answer to our problem is minus 1/3. Okay, what else?
Log 4 x equals 3/2.
Okay, put it in exponential format.
4 3/2 equals x.
Okay. The way I always remember how to put it in exponential is I take the number on the far left, I raise it to the power of the number on the far right, and it's equal to the argument in the middle. So whenever I see this, it's real easy to convert to exponential. It's just this to this power equals that. Now, what is 4 to the 3/2 power? How do we do that?
I don't know.
The denominator is the root. The numerator is, in other words, this is the same as the square root of 4 raised to the 3rd power. Well, the square root of 4 is 2. 2 cubed is 8.
So x equals 8.
Yeah. So x equals 8, exactly. Let's do some more of those. What is this equal to? When they give you these fractional exponents like this, it's always going to be a whole number answer at this point.
Okay. So you take the cube root of 8 then?
Okay, what's that? Again, a whole number.
Into 8?
No, what number multiplied by itself 3 times equals 8?
Oh, 2.
Okay, so cube root of 8 is 2, and then 2 squared is 4.
Oh.
Do another one. It's cube root of 64. Also a small whole number.
4.
Okay, and what's 4 squared?
16.
That's how you do those.
Okay.
And always do the root first. In other words, notice that if I do the square, I can do it in either order. In other words, that's the same thing as 64 squared and take the cube root of it. But notice how much harder it is to do if I do the numerator first. First of all, I got to square 64. I have no idea what that is. And then I got to take the cube root of it. I'd have to use a calculator if I did it that way. But if you take the denominator root first, it simplifies the problem tremendously. Now it becomes 4 squared, and I can do that without a calculator. So just remember that, is don't do the numerator first, ever, on these kind of fractional exponents.
Okay.
When you take the root, you'll almost always get a small whole number. Either
Okay.
2, 3, or 4.
All right.
What else?
Log 4, and then in parentheses 2x minus 3 equals log 4 parentheses x plus 2.
Now, not really going to divide both sides by log base 4. You can't do that. But what is true is if I have the log of one argument equals the log same base of a different argument, then I'm allowed to equate the arguments. Solve that.
So then we just subtract x from the right side and put it in.
Okay. So give me the next line.
So x minus 3 equals 2.
And the next line?
X equals 5.
Okay. Now, with logs, we came up with a solution, x equals 5. A lot of times when you solve logs, you come up with, they end up being quadratics and you get two solutions. And almost always, one of the solutions violates the domain. It's very important to understand what the domain of log is. If I say the log of x, x has got to be positive. It can't even be 0. I cannot take the log of 0. I can't take the log of negative numbers. So the domain of log of x is more restrictive than the domain of square root of x. Square root of x, x merely has to be greater than or equal to 0. But with log of x, it has to be greater than 0. So whenever you're doing log equations, this part here has got to end up being greater than 0. So when I come up with a solution, I want to check to make sure that it truly is. It doesn't have to be. We got log x equal 5. Well, if I plug in 5, I do get a positive number there, so I'm okay there. And if I plug in 5 over there, I get a positive number there, so I'm okay there. If I got a negative number in either side, then this would have no solution. You cannot take the log of a negative number. What else?
Okay.
We'll probably run into one of those, I suspect, before we're done tonight.
Log 2 bracket log 4 parenthesis log 3 x close parenthesis close bracket equals 1.
Okay. Well, you always want to start from the inside. Whenever you have a bunch of nested parentheses, like this, thinking for a moment. Did I write it correctly?
Yes.
Well, I guess I could say that because these two things, oh no, they're not multiplying together. I'm taking the log of the log. Trying to figure out how to do this. I'm not sure I know. In other words, I'm not sure I know how to do this. If I just tried to figure out how to do that, yeah, hold on a moment. Let's see. I think I can figure this out. If we switch this to exponential, then I have 2 equals log base 4 of log of 3 of x, right? In other words, I've taken 2 to the 1 power equals the argument. And the argument in our case is log base 4 of log base 3 of x. See how I got to this?
Yeah.
Okay. Now, let's turn that back into exponential again. How do I do, in other words, let me put the 2 on the other side. Give me the exponential expression of this line. Start with the number on the far left, raise it to the number on the far right, and it's equal to the argument.
So 4 squared equals log 3x.
Okay, 4 squared is 16. And one more time, if 16 is equal to log base 3 of x,
so 3 to the 16th equals x.
and that's your answer.
Okay.
That's a different one. I've probably done one like that before, and I just forgot how to do it. But this is definitely the way to do it, is you just gradually break it down into one exponential expression after another until you finally come up with x equals a number, which is what I did. In other words, I started with the base, the exponent, and the argument. And then I just kept doing that same process. Okay?
Okay, so then there's this one, and it's log 3y minus log 3(2) equals log 3(12).
Okay? As long as we have the same base on everything, then we can apply our rules 1, 2, and 3. Notice rule 1, what it says. Excuse me. Notice rule 2 has log A minus log B. That's equal to log A divided by B.
Yeah.
So let's use rule 2 to convert the left side of this thing into a single log expression.
So then that would be log y over 2.
Right. Oops. And again, if the log of one thing equals the log of another, if they're the same base,
So it's 24.
y over 2 equals 12, y equals 24. Most log equations like this, you're going to have to use one of these 3 rules.
Okay.
You're going to have to either expand or condense. Usually it's condensing one side, compressing it.
Okay. This is log 9x equals 1/2 log 9 minus 1/3 log 9/8.
Log 9, 8?
Yeah. Oh, and I think after the log 9, it's supposed to be 16.
Is this log base 9?
Oh, yeah.
Okay. In your class, how does the teacher verbalize this? Does she say log 9x or does she say log base 9 of x?
She usually just says log 9x, but...
Well, you can see why that's confusing.
Yeah.
Okay, because I don't know how to write it. Because if we were dealing with common logs, you don't say the base. So I would say that's log 9x. So when I talk about logs, I always say base to refer to that. That way it's perfectly clear. Now, I don't think I wrote the right side of this right either. So we have log base 9 of x equals what? 1/2 log base 9?
Yeah, 16
of 16 minus?
minus 1/3 log base 9, 8.
Okay. All right. So what we want to do is compress all of that into a single log expression. Once I have it compressed, then I'm going to have the log of x equals the log of something else, and I'll be able to equate the two arguments. So how do I compress this?
So wouldn't it just be
It's going to take
log,
rules 2 and 3.
so log base 9, 16, or square root of 16 over
Or,
cubed root of 8, so 2.
okay. So over, whoops, hold on a second. Let's do it one step at a time, just so I don't get confused. Right?
Right.
Now, what's that equal to?
Log 9, 4 over 2, so 2.
So x is 2. In other words, I've got the log base 9 of x equals the log base 9 of 2. Therefore, x is equal to 2.
Okay.
Yeah, those 3 rules are huge. Those 3 rules, you can do just about anything you want with logs.
Okay. The next
Couple of
one.
other things to remember. That's always 1. What's this equal to? Always 0,
Oh.
no matter the base. Notice that if the base was 17, it would be 17 to the 0th power equals 1. Any number to the 0th power is equal to 1, no matter what it is. So when I say the log of 1, regardless of the base, it's equal to 0. Okay, go ahead.
Okay, 20 natural log 0.2x equals 30.
Like that, right?
Yeah.
Okay. What's the first thing I can do here?
So it would be 0.2x to the 20th, right?
Well, I'd be tempted to do that. That was my first thought, but that doesn't get us anywhere. I have no idea what 0.2x to the 20th power is. There's another obvious first step here. There's nothing special about logs. This is just a multiplier. If I said 20x equals 30, what would your first step be?
Divide it by 20.
That's what you want to do here also. In other words, if I divide this side by 20 and this side by 20, well, over here I end up with natural log of 0.2x equals 3/2. Now, I can solve it. What's the base for natural log?
Well, e.
Okay, so translate this to exponential expression.
So that would be e to the 3 over 2 equals 0.2x.
So x equals that whole thing divided by 0.2. And you need a calculator to get that number, but that's okay. You know what E is?
Isn't it 2.71?
Yeah. approximately. In other words, that's a non-repeating decimal, a lot like pi. So e is an irrational number. There's no way to write it as a fraction. But 2.71 is a good approximation of it.
I got 4.97.
When you did this? Don't think so. First of all, this has to be greater than 2.7. I'm taking 2.7 to a power greater than 1. And when I divide 2.7 by 0.2, I get a number over 10. So my answer has to be greater than 10. You might have put it in your calculator wrong.
Oh, I got 14.14.
All right, that makes more sense. Always a good idea to do an eyeball check like that. I don't have a calculator, but I knew your answer couldn't be right. Merely if you know that e is 2.7, well, then the numerator has to be greater than 2.7 when you take it to the 3/2 power. What else?
2e to the x equals 10.
First step?
Divided by 2?
Uh-huh. What's the next step?
Would you...
We don't know how to solve that. In other words, you can't put that in your calculator. It's the whole reason that logs were created. The whole science, the mathematic of logarithms, was created to be able to solve exponential functions like that. We know that e to the 1 power is 2.71. E squared is going to be somewhere around 7 or 8. So e to some power equaling 5, this must be between 1 and 2. X is between 1 and 2. But I have no algebraic way of solving it. But I do have a logarithmic way. The rules of algebra say that you're allowed to take the log of both sides of an equation. Well, in this case, I'm going to take the natural log of both sides of this equation. And the reason I do is because when you take the natural log of e, it's equal to that exponent. So x is the natural log of 5. And remember, that's just a number you can get out of your calculator.
I got 1.6.
That sounds right. 1.6. Yep, I knew it was needed to be between 1 and 2, and that's between 1 and 2, so it passes our ballpark test, or our eyeball test. In other words, it's not just e you can do that. If I said 2 to the x is equal to 5, x is also going to be fractional. In other words, x is greater than 2 because 2 squared is 4, but it's not as great as 3 because 2 cubed is 8. So it's got to be between 2 and 3. But I don't have any way of solving this, but I can solve it if I take the natural log of both sides. Now that lets me bring the x down in front. And now I divide both sides by natural log of 2, and there's my answer. X would be natural log of 5 divided by natural log of 2. And again, that's just a number you can get out of your calculator. But that is the beauty of logarithms, is it allows you to solve hard exponential problems like this. And there's no other way to do it. There is no algebraic way to solve this. I mean, there's trial and error. I could start with 2, and then I could try 2.3, and then I could try 2.5, and see how long it took me to come up with a number that got me close to that. But that's awfully inefficient way of doing it. This is why logs were created. What else?
2 to the x equals 27.
27?
Yeah.
Okay. How should I do this?
Uh,
There's two ways to do this. I happen to favor strongly the second way, which is to take the natural log of both sides, regardless of what our numbers are. I'll go through both of them, but
okay.
let's do the first one, natural log of both sides. Now what?
So then put the x in front of the first natural log.
Okay. Now what?
Divide it by x.
Not by x, by the number, by the coefficient of x.
Oh.
Remember, this is just a number. It's a mistake to think of it as anything but a number. Well, if I had a number here, I would finish this equation by dividing by that coefficient. So the answer is natural log of 27 divided by natural log of 2. Okay, you with me?
Yeah.
Now let's go back and do it a different way, which may be the way your teacher even does it. Not any longer or shorter, but I would take the log base 2 of both sides instead of the natural log. And the advantage of that is it immediately reduces the left side to x. Because remember, the log base b of b to any exponent is that exponent. The problem is that it doesn't really help that much. There's my answer, but you can't get that out of a calculator. You have to apply the change of base formula. Well, the change of base formula is the log of the top number divided by the log of the bottom number. And when you're dealing with ratios like that, doesn't matter what log. In other words, that ratio is the same ratio as the natural log of 27 divided by the natural log of 2. That's the answer we got the first time. In other words, I can condense it to get this in one step shorter than I did the other method, but then I got to change of base that. So it adds that step that I saved back, and it ends up not being any shorter at all. And the disadvantage is you have to know the change of base formula. If you don't know the change of base formula, you don't know how to handle that. So all of that goes away if you take the natural logs of both sides. In other words, if I take the natural logs of both sides, now the left side doesn't become x. It just allows me to bring the x down in front, and now I don't need the change of base formula either. I get immediately x equals that divided by that. And the natural log is the log function for calculus. Once you get the calculus, you hardly ever use any other log other than natural log. And so the sooner you get comfortable with it, the better.
Okay, I got 4.75.
I don't even care what the answer is. That just means you looked it up in a calculator. It's getting to that answer that's important. In other words, it's getting to that natural log of 27 divided by natural log of 2. When you get to that point, you've got it solved. The rest is just getting your calculator to tell you what that number is. And I know you need that number for your material, your test or your homework or your quiz or whatever, so it's not irrelevant, but as far as our tutoring session, I don't care what it is.
Okay.
It's not relevant to understanding the problem.
This one is 5 to the 2x equals 9 to the x minus 1.
Okay. What should I do here?
Could you take the natural logs of both sides?
That's a good start. And the reason it's a good start is because our variables are in the exponent. When your variable is in the exponent, it's no longer an algebraic equation. And it can't be solved algebraically. It can only be solved through logarithms. Okay, now that I've taken the natural log of both sides, what?
So then it's 2x natural log 5, x minus 1 natural log 9.
Make sure you use parentheses here, because it matters. Okay, now what do you suppose the next step is?
Well, could you divide by 5?
No. You could divide by natural log of 5. In other words, you can't separate the 5 from the natural log. This is not natural log times 5. This is natural log of 5. It's like f of x. F of x is not f times x. It merely means it's a function with x as the variable. Well, this means natural log of 5. But always remember these are numbers. Okay? If I gave you an algebra problem like this, how would you solve it?
Put the 5 on one side.
No, you need to distribute the 5. In other words, the first step of solving this, I can multiply that together to get 6x, but it's equal to 5x minus 5. Now I've moved the x over and I get x equal to minus 5. Okay, so you need to be able to solve this kind of an algebra problem before you can solve this one. Because notice there's no difference. I've got 2x times some number, and I've got x minus 1 times some number. So I have to distribute both of these. I don't need to distribute that yet, and I'll show you why. But I do need to distribute this. So that would be x natural log of 9 minus natural log of 9. Over here, we got 2x natural log of 5. Now what do I need to do to solve this equation?
Could you put, wait, do you...
Gather all terms that have x in them on one side of the equation, everything else on the other side.
With,
Notice that that's what we did when we used numbers instead of logs. So I distributed, and then I gathered all the x's on one side and put all the numbers on the other. So let's take this term, put it on the left side. What do you get?
Then you get x natural log negative.
We get this. To put it on the other side, I got to change its sign. Right?
Okay.
Okay. Now what? Factor out an x. In other words, this isn't quite 6x minus 5x, but it is, really. I mean, I don't know what this number is or what this number is. I could put in those numbers and then do it, but then I wouldn't have an exact answer. I would have an approximate answer. But if I factor out the x, notice what I have left. With me?
Yeah.
That's just a number. Therefore, I can divide both sides by it. That is a number also that you can get out of your calculator.
Okay.
Okay? And again, I don't need to know what that is. If you need it, go ahead and put it into your calculator now and come up with an answer. But this is a little tricky. This whole problem was a little tricky. And the only reason it's tricky is because people really get thrown off by this natural log of 5. They forget that it's a number. As long as you remember that's a number, then you would solve this in the same way you would solve an algebra problem. If I gave you the following algebra problem. First thing you'd do would be to subtract 1.3x from this. But there's two ways I could do that. I could do it the following. You with me?
Mm-hmm.
I'm going to factor out an x now. I'm not going to do this subtraction. I'm going to factor out an x, and what's left behind is 3.5 minus 1.3. Now I'm going to divide both sides by this. 3.5 minus 1.3. So I'm able to solve for x without doing that subtraction, merely by factoring out x. And when you're dealing with logs, when you have logs in place of numbers here, in other words, when I have the log of 5, I can't do this math. I don't know what 2x natural log of 5 minus x natural log of 9 is equal to, because I don't want to convert these to a decimal yet. If I converted this to a decimal number, then I could do it, but then I'd be dealing with rounded off numbers. You don't want to round off these numbers. You want to leave them precise. So I always want to leave this as natural log of 5. If you were giving your answer to this problem to a college math class, it would not be a number. It would be this, what I have circled at the bottom. That would be the answer. You would not turn that into a number, because the moment you turn it into a number, you've made it less accurate. These are irrational numbers. It's like turning square root of 2 into 1.4. You don't do it because we're rounding it off when we do that. We leave it as square root of 2. Same thing with logs. And it's critical with logs because if I knew what that number was, I could subtract x log 9 from that number. But I don't know what it is, therefore I have to solve it by factoring it out. And then I can give a totally precise answer. It's kind of like when they say, solve these problems and leave your answers in radical format instead of decimal. Same principle. When you leave it in radical format, it's more accurate.
Okay.
What else? Got about 10 minutes.
Log 6, or log base 6, open parenthesis, log base 4, open parenthesis, log base 2, x, close parenthesis, equals 0.
Okay, let's do it the same way we did the other one. Turn it immediately into an exponential expression. In fact, do it 2 times, 3 times in a row, and we'll have our answer. So what's the exponential expression for this log expression?
Log,
Remember the number on the far left.
6 to the 0 equals log base 4 log base 2x.
What's 6 to the 0 equal?
1.
Turn it into another exponential expression.
So then 4 to the 1 equals log base 2x.
Turn it into one more exponential expression and you'll have your answer.
2 to the 4th equals x. Okay.
That's actually pretty easy to do considering how tough the problem looks.
Yeah, you'd think it'd be harder than that.
No, you would. Yeah, I know. I haven't seen one of those in a while, but I forgot that they really solve quite easily.
Yeah.
As long as everything's a nice whole number. And they're going to be at this stage. They're not going to give you too many that don't result in whole numbers, at least not problems like that.
That's good. Alright, log base x 27.
Log base x?
Yeah.
Okay.
27 equals 3 over 2.
Okay.
So then it would be x to the 3 over 2 equals 27. So then it's x squared, right? Or x, square root of x. Or wait.
How can we turn the left side into x?
Divide it.
No. It wouldn't result in x if I divided it. However, if I exponentiate it to the 2/3 power, notice what happens on the left. You multiply, whenever you're doing a double exponentiation like this, you multiply exponents. Well, this becomes x to the 1. Since I took the left side to the 2/3 power, I got to take the right side to the 2/3 power. Left side is x. What's 27 to the 2/3 power?
So you do, so it'd be 18?
No, it's cube root of 27.
9.
No. Remember, it's always a little number.
Oh,
Cube root. It's a number multiplied by itself 3 times that
3.
equals 27.
3.
Okay. And what's 3 squared?
9.
Again, they're not gonna, if they give you something like that, you can bet it's a whole number answer. It's not going to be a fractional, decimal answer. They're never going to give you this. Now you got to use a calculator to get that. And these problems are designed to be solved without a calculator. At least these problems. The problems where we ended up with answers that looked like this, you need a calculator to solve that. But okay. What else?
Log base 3, open parenthesis, x squared minus 7, close parenthesis, equal 2.
Okay. Next
So
step.
then 3 squared equals x squared minus 7. X, 15 equals x squared. Four.
Plus or minus 4. And that's something that virtually every single student leaves out the plus or minus, and you can't leave it out. Minus 4 times minus 4 is equal to 16. Plus 4 times plus 4 is equal to 16. Therefore, if 16 equals x squared, x has to be plus or minus 4. Now, we got two answers, and that's fine, and neither one of them violate a domain. Notice that even if I use minus 4 in here, I'm squaring it, so it becomes 16 minus 7, taking the log of 9. And if I use plus 4, it still becomes 9 in the argument. So both answers work here. However, I won't give you the however. For one thing, I don't have enough time. I have an 8:15 I have to do also.
Okay.
So I got maybe time for one more.
That's okay. That's really the last one I had.
Yeah. Okay.
Yeah.
Well, I hope that was helpful. You feel it feels to me like you understand it and you know what you're doing.
Yeah. I'm mostly, yeah.
Okay. All right, Jade. I will talk to you. Let's see. Are you in school next week?
No. So yeah, I shouldn't. I don't really, and I get my wisdom teeth out, so I don't need that one.
I will cancel the appointment on the 25th, and I will talk to you the first week of December.
All right. Sounds
Let me
good.
just make sure I have you in. Yeah, I do. At 7:15. Okay.
All right. Sounds good.
Talk to you later. Good luck on your wisdom teeth. Have a nice
Thanks.
Thanksgiving also.
Thank